then there are times when it will prove to be a bit difficult. So in such a case, that's when we use the matrix method.
Yeah.
So that's when we use the matrix method. So today we'll
are recording?
Yes, I am.
Okay, thanks.
Okay. Let me just confirm if it's okay. Okay, so that's when we use the matrix method. Okay, so with the matrix method, first thing first, from the ordinary least squares method, we know there that our y is equal to a beta naught plus beta 1 xi, then plus the error term. Okay, but in the matrix method, it's the same model, only that now we'll be denoting it as y is equal to xb plus the error term. There's no difference between the two. Okay, what we are seeing is that with the matrix method, there is a vector containing y values, okay, from y1, y2 up to yn, okay, and these y values are equal to, right, then we have another matrix that is containing the x values. So x1 from observation 1, okay, then we've got x2 from observation 2, just like that, up to xn or xk from up to xk, like this. So let me say xk for observation 1, like that. This thing is tripping, don't know why. Okay, why is it doing this? Okay, so in this case, so we have a vector y containing the y values, which must be equal to a certain matrix, and this matrix is the one that is going to contain the explanatory variables, the x values. So we've got x1 here for observation number 1, we've got x2 for the same observation up to xk. Okay, then we have got again x1 for observation number 2, we've got x2 for observation number 2, and then we've got xk for observation number 2. This goes on until we have all the x values. Okay, so x1 for n, we also have x2 for n, up to xk for n. In short, we're still using the same model, only that now we want to present these in form of matrices. So our y, this y here, is this vector containing the y's, and then the x, they are contained in this matrix, and then we have to multiply this matrix by another vector which should now contain the betas. Okay, should contain the betas, beta 1, beta 2, up to, like that, up to beta k. Okay, so this we are saying plus the error term. So the error term will also be contained in a given vector from error term 1, error term 2, up to error term k or n. Okay, so what we are saying is that we're using the same model, y is equal to xb plus the error term. So this y is a vector of y variables. This x is going to be represented by a matrix of of the explanatory variables, and then for the b's, the betas, we are going to have a vector that is going to contain all the betas, okay, and then plus the error term. So again, the error terms will be contained in a given vector from error term 1 up to error term n. Okay, so what we can see is that when we try to open the brackets, we'll still go back to the same model, this one. Okay, so we know that, for instance, this y the first y there, we can say that y1 is equal to we can start multiplying. Now remember, with matrix multiplication, it's row by column. Okay, so it means that this x1 will multiply by that beta 1. Okay, this x2 will multiply by that beta 2, and that xn will multiply by the beta k. So we said at the end of the day, we'll still get back to x1 multiplied by beta 1 plus x2 multiplied by beta 2, just like that, plus xk multiplied by beta k, which will still be plus the error term. When simplified, this will still give us yi is equal to xb plus the error term. Right. So now what we want to work with is this guy here. The yi is equal to xb plus the error term, which is the matrix representation of the regression function. Okay, so yeah, so we're going to work with the yi is equal to xb plus the error term. Okay, so we know that in our regression, or in any regression model, we can either have a basic model. Okay, we can have a basic model, or there are times when we can have the multivariate model. Alright, and with the basic model, this one is just, it's one which is, let's say, yi is equal to just beta 1 xi plus the error term. Maybe we can include the maybe we can include the constant, so beta naught plus the beta 1 xi. This is a basic model. But with a multivariate, we are going to have a lot of explanatory variables. In short, if you have got two explanatory variables, such a model qualifies to be called multivariate. Okay, but if you have got one explanatory variable, let's say just one x, let's say it's just x1, then we include the error term, then this is just a basic model. Alright, this is just a basic model. But if we have something like, let's say yi is equal to, let's say beta naught plus beta 1 x1 plus beta 2 x2, then let's say plus the error term, even if we are only having two explanatory variables x1 and x2, the fact that these explanatory variables are more than one, this model qualifies to be called a multivariate model. Okay, yeah, so this qualifies to be called the multivariate model. So anyways, I just thought of discussing this, that we've got two types of models. There's the basic regression model, and then there's the multivariate regression model. Alright, yeah, so let's go back to our matrix representation. So now we are saying that we are going to work with this model here, yi is equal to xb plus the error term, where the yi is just a vector containing the dependent variables. Okay, then the x is going to be a matrix containing all the explanatory variables, and then the beta here is going to be a vector containing all the betas. Right, and then the error term will also have its own vector that is going to contain the explanatory variables. Okay, yeah, now remember that we are saying that yi is equal to xb plus the error term. Right, now we know that, just like we discussed under ordinary least squares method, that there are those deviations, because we cannot work with the sample, we cannot work with the population. We're going to work with a sample, and now as we're working with this sample, there are those deviations between the the sample and the true population regression function. All right, and what we want is to minimize or to reduce those deviations, right? Yeah, what we want is to reduce those deviations so that this sample that we're working with should be a perfect representation of the entire population, right? Meaning that the error term, the EI there, is just equal to y minus xb. Okay, in short, can we make the error term the subject of the formula? Okay, so now we know that this error term is it measures the deviation between the y and the xb, between the dependent and the variables that are explaining this variable. Okay, in short, it measures the deviation between the between the dependent and the independent variables. Okay, so now what we want is to minimize this error term. Okay, what we want is to minimize this error term. But now, hi.
Yes, George. The deviations.
Yes.
These are also called the residuals.
Exactly.
Okay.
Yeah. So these are also called the residuals. Correct. These are also called the residuals. Exactly. So what we want is to minimize these residuals. So we want to minimize the residuals. So now, how do we use matrix method in order to deal with these residuals, right? How do we use the matrix method to deal with these residuals? So now we are going to define a function L. Okay, we are going to define a function L where this L is going to be a function of the residuals. But how? These residuals will be we are going to have E transpose multiplied by E, where E is the error term. Okay, so going back to matrices, we know that if we've been given a function, let's say A, right? Let's say A is equal to maybe 1 and 2. To find the transpose of this, the rows will become the columns will become the rows, meaning that the A transpose will just be 1, 2. Okay, so the column has now become a row. Okay, so we are going to use this concept of transpose of a matrix. Okay, so we're going to use this concept of transpose of a matrix. So what we know is that if the error term is a vector, if there's a vector somewhere that is containing the error terms, right? So let's say that our vector that is containing the error term looks like this. We've got error term 1, error term 2, just like that up to error term n. Then it means that the transpose of this is going to be error term 1, error term 2 up to error term n, like that. Okay, so we are saying that first thing first, we should define a function L, and this function L should be a function of the E transpose E. Okay, where E is the error term, and this error term is the residual. Okay, is a residual, which is the difference between the true regression function and the sample regression function. Okay, so now what we also know is that this thing E transpose E is just, or it can be represented as because our E, the vector that is containing the residuals, is this one, and its transpose is that one, meaning that E transpose E, okay, will just be the transpose, okay, which is this this one here, error 1, error 2 up to error n. Okay, we are saying that let this transpose be multiplied by the original vector containing the error terms up to error term n, right? So we know that, well, with multiplication of matrices, E transpose E, it's more like you're multiplying E transpose times E, where each of these contains some values, right? And it's just row by column. So it will be this row multiplied by this column, meaning that we'll now be multiplying this error term 1 will multiply by that error term 1. Okay, again that error term 2 will multiply by that error term 2, and that error term n will also multiply by that error term n. So it will be like error term 1 times e1 there. This will give us e1 squared plus error term 2 times error term 2. This will give us error term 2 squared. So this will keep going until the last en squared. What does this mean? This basically means that if I get the error term, the transpose of that error term times the original error term, this is just more like I'm summing up these error terms from I is equal to 1 to n of ei squared. You see? So in short, E transpose E is just a summation of the squares of the error term, which is similar to what we are doing under the ordinary least squares, because remember there we said that those deviations, if you just get them, if you just get y minus actual y minus y beta, if we just get those deviations and put them together, they'll give us a 0. So to avoid getting the 0, no wonder we are squaring those deviations, which is more like the same thing that we are doing right now. We are still squaring the deviations. We are still squaring the residuals, because the sum of residuals is a 0. Okay, when you get all those residuals, you put them together minus squaring them, you're going to end up getting a 0. And what we don't want is to get that 0. No wonder we are going to square those deviations. We're going to square those residuals. So this process here, ei squared there, it's the same thing that we are doing yesterday. We were saying y minus yi hat squared. We called this as the ei squared. Okay, so this is just more like what we are doing right now. Okay, great. So now can we go back to our notation? So what we know is that this error term is y minus x beta. Okay, so this error term is y minus x bar, but what we want is to square these. How do we square this? Is to multiply ei, or is to multiply this e transpose e, because you know that after multiplying e transpose e, we are going to get the squares, the sum of squares. Okay, so this then means that since ei is y minus xb, okay, since the residual is equal to y minus xb, and for us to square these residuals, we should multiply e transpose times e itself. This then means that our e transpose is going to be y minus xb, this transposed represented by t, okay, multiplied by the actual y minus xb. So if e is equal to y minus xb, then if we want to square these residuals, we have to get the transpose of e and multiply it by the original e. Alright, and our e transpose is this one in the brackets here, y minus xb transpose. Alright, so it's this is the e transpose, okay, e transpose, and then that last term there is the e. Okay, so this is the e transpose e. Okay, so what we want is to of course is to find a set of betas that will minimize these deviations, just like we are doing under ordinary least squares method. Okay, so how is it up to this point?
It's clear, George.
Okay, that's great. Yeah,
Yeah.
that's great. Yeah, so after
kako.
Mama,
Now this looks like also you have used Bemba. I'm saying this one looks like a more straightforward kind of procedure.
Oh, I see. Let's see if I pray that it should be like this throughout.
Please.
Yeah, okay, great. So the next step after E transpose E, the next step is just to distribute the transpose. Okay, so can we distribute the transpose? Okay, so distribute the transpose. Okay, so what it means is that we should now distribute this T there, we should distribute it throughout in the brackets here. Okay, so this will be Y transpose, okay, after opening the brackets, Y transpose, okay, minus X transpose B transpose. Okay, so this is being multiplied by Y minus XB, like that. Okay, so this is still E transpose E. Okay, so that is still E transpose E. Now from here we just have to open the brackets. Okay, so the next step there is just to open the brackets or multiply throughout. Okay, so open the brackets, which is just multiplying throughout. So now we'll be multiplying this YT, this Y transpose, times everything this side. Okay, then again the XT BT should also multiply by everything the other side, just like that. Okay, so Y transpose times Y. Okay, Y transpose times Y, that will give us Y transpose Y. Okay, yeah, so that will give us Y transpose Y. You see that? The same Y transpose, can we multiply it with the negative XB on the other side? So that will give us minus Y transpose XB. Okay, then now we come to this other term here, this one, the negative X transpose B transpose. It should also multiply by everything in the other brackets there, right? So negative X transpose beta transpose multiplied by Y, that will give us minus Y X transpose beta B transpose, like that. Okay, those are transpose. Let me just write this properly. Yeah, so transpose there and transpose there. Okay, then negative times negative there, that's a positive. Okay, then X transpose B transpose multiplied by XB, that will just be plus X transpose B transpose XB, like this. So this is still E transpose E. The only thing that we've done here is just to distribute or to multiply throughout, so that we can open the brackets and have one single equation. Okay, yeah, so we've got this now. Now there's something worth noting here, and that is that if you look closely, if you pay attention to this term and also this term, there is some form of similarity there. How? When we get YTXB, okay, when we get this and transpose it, it will give us the other term here. It will give us Y X transpose B transpose. How? Can we distribute the transpose on the other side, on the left hand side? Yes, we can. So Y transpose is just Y. In short, the transpose will cancel, the T's will cancel. So that will just be a Y. Okay, then that transpose by this X, that will be X transpose. Then this B transpose to give us B transpose, which you see is equal to the guy on the right, which is y x transpose b transpose. So you see there is a relationship between A and B there, that just transpose of each other. Okay, so the two terms are transpose of each other. If you get this term A, you transpose it, you're going to get B. If you get B and transpose it, you're going to get A. So there's some form of relationship that is existing there. In short, since this term here, y transpose x b, if we transpose it, it's going to give us y x transpose b transpose, then shows that the two are equal. Okay, the two are equal. Okay, so since y transpose x b, if we transpose this term, we are going to get the other term, then they're just transpose of each other. Okay, which means they are related. There is some form of relationship that is existing between term A and term B. Okay, so there is some form of relationship that is existing between term A and term B there. I just want to be sure if this concept is okay between A and B.
Yeah.
Okay, great. So now, if y transpose xb, that term transposed, is going to give us is going to give us term B, then we can substitute. Okay, we can substitute. Okay, in short, we can just say that, okay, if this is the case, then it means that y transpose xb, okay, is just equal to this guy on the other side, because we just have to transpose this guy. Okay, we just have to transpose this guy, and we're going to get the other guy. So in short, after reaching this side, we can say, can we substitute? So substitute. Yeah, so substitute the term x. Which one? Okay, yeah. So we have to substitute A into B. In short, we can get A into B or B into A. We can substitute A for B or B for A, because we've said that there is some form of relationship that is going to exist between the two. Why? Because we've said the transpose of term A will give us term B, and the transpose of term B will give us term A. Okay, so we can substitute X transpose, which is which one now? Yeah, so in short, we can substitute B for A. Okay, we can substitute B for A. Okay, we can substitute B for A. Okay, and now when we do that substitution, right, look, it will be like this. E transpose E is equal to, we get the first term there, y transpose y minus. Okay, so minus, this will give us, we are going to have y transpose xb, which is this term. Okay, y transpose xb here, which is that one, and then while there is b there, we can put A. Why? Because the two are equal. So where there is B, where there is that whole term there, we can also put minus y transpose xb. Okay, then we add the other term there, the x transpose b transpose xb, like that. Why have we done this? It's because we have established that the two are transpose of each other. So whether I get A, I transpose it, I'll get B, or if I get B and transpose it, I'll still end up getting A, meaning that the two are just equal to each other. So therefore, where there is B there, I can put A. Okay, so where there is b there, I can put a. Okay, so if this is the case, then we can now say that this term is equal to that term. Okay, so if that's the case, it means that E, which is E transpose E, will be Y transpose Y. Okay, Y transpose Y. Then it's more like I've got something like this. Y is equal to, let's say, negative x minus x. This is just negative 2x. Right? Minus x minus x. This is just negative 2x. So which means that since the first term, this guy here, okay, that guy there, is, we are saying minus the same thing. Okay, so negative, negative, it's more like we're saying negative 1 minus negative 1, which is going to give us negative 2. So this means that simplifying the two terms is just going to be minus 2 y transpose xb, right? And then we add that term there plus x transpose b transpose xb. You see that? So why have we done this? It's because we can do the subtraction there, and the two are equal, you know. So it's like I say minus 1 minus 1, which is minus 2. All right, how is this concept?
Fine.
Okay, great. Yeah, which means that now we can simplify our thing and say, can we let this E transpose E equal to L? Okay, so that while there is E transpose E there, we can just put letter L. So letter L is equal to Y transpose Y minus 2 Y transpose XB, okay, plus X transpose B transpose then XB. Okay, now remember, when we are doing the ordinary least squares, we reached at a point where we had L, and we are saying this L is a summation from I is equal to 1 to n of y minus yi squared. Okay, which was something like L is equal to the sum from I is equal to 1 to n of, we had y minus beta naught hat, then minus beta 1 xi, right? This was being squared, and then we said, okay, from this can we get the partial derivatives with respect to beta naught hat, and also another partial with respect to beta 1 hat, right? So now it was after doing this that we got those partials, and then we, you know, simplified and got the values of beta naught and beta 1. So that step or that point is this point here, where we have the L, where this L is equal to the residuals. Okay, the residuals is squared, which is that stage there under order least squares. Okay, so in short, the next step here is to do the partial derivatives. Okay, so the next step there is just to do the partial derivatives. Okay, you should have to get the partial of L with respect to beta. So one thing, what you should always remember is that in this case, don't think as beta as one, let's say one variable beta naught, or maybe one variable beta 1. Think of it as a vector, because these are matrices. So everything here, these are vectors we're working with right now. Okay, so the y transpose there, just want it's a transpose of vector y. Okay, so the y transpose there is a transpose of vector y. Where this b, just know that b is a vector containing the betas, right? So it's a vector containing the betas. So just think of it in those lines. So these are vectors. So don't think of them as just, let's say, beta 1 or beta naught as just one variable. It's in a set of betas, you know, in a given vector. So it's something like this. So while there is this, like that y there, these are y's from y1, y2 up to yn. There, where there is y transpose, given that this is y, right, then y transpose will be the other way around. Now it's a transpose, so the columns will now become the row, like the y2 up to yn, like that. Okay, so everything here should be represented in that form, or just picture this thing. Yeah, okay, that will really help with understanding the, like, what's going on. Okay, great. All right, so now can we simplify? In short, can we get the partials? Yes, we can. Only that we need to discuss a few rules about differentiation of matrices. Okay, how do we differentiate matrices? So it's different from the way we differentiate normal equations. Okay, it's different with the way we differentiate normal equations, because these ones here are vectors. Okay, so they are just three basic rules that we use to differentiate vectors. Okay, the first rule, it goes like this. So let's say rule number 1. With rule number 1, it states that if I have a function, so if I've got vectors, sorry, if I've got vectors, okay, and these vectors are represented like this, like C transpose Z, okay, C transpose Z, where the variable of interest in this case is Z. Well, let me just do this. Where there is Z, let's put T B, because that is what we're working with here. Okay, so C transpose B, what we want is to get a partial with respect to B, right? So it's more like we are differentiating C transpose B with respect to B. The answer, okay, the answer is just a C. Okay, the answer is just a C. Now, what is C? In this case, the variable, or the vector of interest is B. No wonder we're differentiating with respect to B. So if we want to differentiate with respect to B, the answer will just be, in short, it's more like we're going to get this C transpose, but get its C. In short, we're just going to find the transpose of the C. Okay, so that is the first rule. Let me just explain it again. So rule number 1 states that if we have a variable, a vector, right? If I've got a vector, C transpose multiplied by another vector there, B, and we want to differentiate this with respect to vector B, the answer will just be C transpose transpose, which is just a C. So the answer will be the transpose of the other guy, and we know that if we get C transpose, we'll get a C, right? Now maybe you're wondering, what is the application of this? We want to use this and do the differentiation for this L here. Okay, for this L here. Okay, so that's the first rule of differentiation of vectors. Okay, how about the second one? The second one, I think it's the simplest. So rule number two, this one states that if I have a vector, okay, if I have this combination B transpose AB, I want to differentiate this with respect to B. The answer will just be 2 multiplied by A and B. Okay, so if I've got B transpose multiplied by AB, right? B transpose multiplied by AB, if I want to get the derivative of this with respect to b, vector b, the answer will just be 2 multiplied by vector a multiplied by vector b. So we are just going to use just these two to do our differentiation here. Okay, right. How are these, ma'am?
Okay, George, except I managed to avoid the 2.
Except?
What have we done 2?
So 2 is more like there is a separate arrangement of showing how to get the 2, which is a session on its own. So in short, take it as 2ab is the present truth, like it's part of the formula, like something like that. Okay, but in detailed matrices we show how we arrive at this. Okay, that's okay.
Okay.
Yeah, great. So we're just going to use just these two rules. Now let's check our function. Let's check our thing there, if we can apply these two. Okay, first thing first, remember with partial derivatives we differentiate those terms containing that particular variable that we want, right? In this case, for the first part there is no b, which means this is just like a constant. We're not going to tamper with it, we're just going to forget about it because there is no b there. Okay, but for the second term there is b, which means this one has to be differentiated. For the other term there is b, which means that term also has to be differentiated. In short, for the first term it's just more like it's just a 0 because there is no b there, so we're just going to consider it as a constant. Okay, meaning the change in L with change in b is going to be, let's start with this guy here. Okay, that guy there. What do we have there? We have, so sorry if you're hearing noises, the other side they're praying. Yes.
Oh, during the day it's fine. I understand.
Yeah. Okay. Yeah. Okay. So this part, which is minus 2 ytxb, right? Can we differentiate this term? Yes, we can. Now check this out. We can consider this first thing there, this the negative 2ytx, okay, as the C transpose, okay, as the CT, and then this B here as our B of interest, okay, as our B of interest. What does this mean? This means that if I want to get the derivative of just this part here, my answer should just be, remember, it's more like we're using the first rule of differentiation. Okay, it's more like we're just using the first rule of differentiation, that if I'm differentiating this CTB with respect to B, my answer will just be C. You see that, right? So in this case, this will just be the derivative of the first part. It will just be negative 2, okay, y transpose x, but this has to be transposed. Remember, there is something that I've said when explaining the first rule there, to say that the answer will be C, yes, but check, the initial thing had C transpose, and we are saying that the answer should be C. What does this mean? It means that this C transpose has to be transposed, because it is only after transposing the C transpose that will get the C. Okay, in short, we're just applying the first rule of differentiation. Okay, where we have C transpose, which is this whole term negative 2ytx, right? This thing then multiplied by B. Okay, so if we want to get the derivative of b from this term here, the answer will just be c transpose, the answer will just be this term but now transposed. Okay, meaning that the derivative of the first part there with respect to b is just this term here. Okay, how is that, ma'am?
Fine.
Oh, great. Then with this part here, there now we're going to use the second rule of differentiation. Why are we using the second rule of differentiation? It's because, let's look at the order. The second rule is telling us that if I've got b transpose ab, we want to differentiate this with respect to b, right? So let me just rearrange this like the one in the second denominator. That term is more like we are saying the same thing, like saying b transpose x transpose, right? X multiplied by b. It's just a matter of arrangement. Remember, this is multiplication. With the multiplication, the order of arrangement like doesn't matter. 2 times 2 times 3 is still 3 times 2. Okay, so now in short, with a second term there, sorry if you ish, I wish I can. Are you distracted?
No.
Okay, great. Okay, great. Yeah, so b transpose xb, if we want to differentiate that term there with respect to b, we know that this b transpose is this b transpose in the function in the formula. Then the x transpose x is the a. Okay, then this b here is that b there. Okay, meaning that if we want to differentiate that term with respect to b, the answer should be 2 times a, where what is our a? Our a is the x transpose x there as our a. Then this c is our b transpose, then that b is there, is this b there. Meaning that the answer, we are saying the answer should be 2a times b, right? Which would just be 2. What is our a? Our a is x transpose x. Okay, then what do? We put back the b, because this is what the formula is telling us, that the derivative of that part should be 2x transpose x b. Where is the 2x transpose xb coming from? It's because this 2 is for the formula, then the x transpose x is the a in the formula there, that's our a. Then this b is that b there at the end. Okay, meaning that our answer for the last term will just be 2x x transpose x, then we put back our b. Okay, that's okay, right?
Yes, George.
Okay, great. So therefore, change in L due to change in beta is just going to be, now can we distribute the transpose sign? This comma 1 now this side. We know that the 2 transpose will still be 2. Okay, so this will just be -2, but now y transpose is just a y. Okay, in short, transpose of a transpose is the original thing. Okay, so if we say a transpose, the answer is a. Okay, but now this x has got no transpose, so when we put the effect of the transpose, the x will now become transpose, and then plus this other guy 2 x transpose x b. Okay, now after reaching this stage, remember that every time we differentiate a function, we equate it to 0, right? Which means that -2 yxt, right, plus 2x transpose x b is equal to 0. Okay, yeah, we've got this. Okay, so the next thing there is just to get like terms together. Okay, you just have to get like terms together. What am I saying? No, just get the other guy, like this guy, to the other side, so that we can factor out b. Remember, what we want is to make this b here, this b, the subject of the formula. That is what we want. Okay, so let's just take the other term to the other side of the equation, so that we're going to have, on the left hand side, we're going to have 2x transpose x b, right, is equal to, this guy is negative. When it crosses the equal sign to become positive, so it will be now 2y x transpose. Okay, yeah, something like that. Great. Now look, if it was normal equations, right, like normal functions, let's say we've got 2xy is equal to, let's say maybe 7z. To make let's say to make x a subject of the formula, would have just said, okay, can you divide by 2y this side, we also divide by 2y this side, so that those two can cancel, then we remain with x a subject of the formula, right? But with matrices, there is no such thing. In short, you cannot divide matrices. Okay, so matrices cannot be we can't divide matrices, which means that for us to make b the subject, we need to do some just a little form of manipulation. How? When we introduce the inverse of, so in short, if we say we multiply, so in short, if we multiply both sides by a half, okay, x transpose x inverse, okay, then because look, x transpose x inverse, it's more like we are saying half x transpose x inverse, it's more like we are saying half it's more like we are saying 1/2 multiplied by 1/x transpose x, like this, then to the power 1, right? Which is more like, in short, it's more like we're taking this term x transpose x in the denominator, but the rule is that we cannot divide matrices. So what do? Just introduce the inverse. Generally, it's more like we're dividing, but you cannot divide matrices. It's against the laws of mathematics. You cannot divide matrices. So the only way that we can make b, or the only way that we can make b to be alone on the left hand side, is if we multiply both sides by half. If you multiply by half, then x transpose x inverse, like this. Okay, so why are we doing this? We know that if we multiply both sides by half x transpose x inverse, this will be like these people. Okay, great. Yeah, so we said that we should multiply both sides by a half, okay, by half x transpose x inverse, so that we can make beta there the subject of the formula. So this will be, half is 0.5, right? So it will be 0.5 multiplied by x transpose x inverse. This is being multiplied by 2x transpose x b, that's on the left hand side, right? So this should be equal to, we should do the same on the right hand side. So we should also multiply the right hand side by 0.5 x transpose x inverse. This should be multiplied by 2y x transpose, like that. So what we've done is just multiplying both sides by 0.5 x transpose x. Now, what is the impact of this? The impact is that when you multiply 0.5 times 2, it will be 1. okay, to be 1. And then x transpose x inverse, if we multiply this by x transpose x, the answer will also be a 1. In short, everything will cancel, because it's more like we're saying 2x transpose xb divided by 0.5. Oh yeah, so let's say 0.5 is this side, we are multiplying, so divided by x transpose x, but we don't want to divide, but the logic is the same. So it will be this 0.5 times 2, the answer will be a 1. So in short, this and this will give us a 1. Then now we'll just cancel, meaning that we just remain with a b on top, which is what we want. But you cannot divide the matrices. So how do you handle that? It's by introducing the inverse. Okay, so it's by introducing the inverse. So at the end of the day, on the left hand side, we're just going to remain with the b. Okay, now on the right hand side, we're going to multiply. Now this is 0.5 times that 2, the 2 will just give us a 1. What does this mean? This means that b, in short, the final answer of everything is just okay, the final answer of everything is just x transpose x, this thing inverse, multiplied by that, because the 2 and the 0.5 will go, right? So this will be multiplied by y x transpose. So the final answer is x transpose x inverse multiplied by x transpose y, like this. So here I've just changed the arrangement, but it's okay. The answer is still the same because this is multiplication. So our answer is this: x transpose x inverse, then x transpose y. So in short, we'll be working with this. Given a question that is talking about matrices, or that uses matrices and all those things, if we want to get the values of beta 1 and beta 2, we are just going to be using this gamma function here. X transpose multiplied by x, then you get the inverse of that, then you multiply by x transpose y, then you are done. So what I want is this: since we've looked at how to get this beta, what I want is to find a way now of putting this beta into action. Okay, so because tomorrow I'll be busy, Wednesday I'll also be busy. Those are my busy days. So if it's okay, let's meet on Thursday anytime.
Thursday.
Yes, Thursday anytime, where we are going to look at the seminar questions. I think among the seminar questions you sent, I saw something that has got everything to do with this function